Hey guys, we were receiving multiple grievances about the sound quality from multiple viewers over a long period of time. It took our serious attention. As a solution, we are republishing the UPF episodes by digitally remastering the audio. In this video, we have clubbed 6 episodes from the UPF series to cover the entire UPF in detail. So stay tuned, stay focused. Hey guys, welcome to the first episode of UPF Unified Power Format, and in this episode, we'll discuss UPF in today's chip design scenario, how UPF is placed in SOC design, what is UPF in detail, 3 major types of UPF annotations, standard UPF terminologies, UPF integration in various design stages, 4 major type of UPF command. So guys, this is the menu for today, and without any further delay, let's begin. The scenario of today's chip. So this is basically one structure here, which we can just imagine. Today's many advanced chips will have their inside. So we have multiple voltage domain, like here VDD1 is there, here VDD2 is there, here VDD3 is there. Okay. It could be a digital block, analog block, a macro which you have ordered from any IP vendor. So this could be different blocks inside your design, and there can be one power management block. Because in today's chip, most of the chips are going in the direction of the analog mixed signal. So multiple blocks will be there. So the VDD for the analog block and the VDD for the digital block will be very different. And macro is certainly coming from an IP vendor. It might have a different VDD. So these are various power domains. To take care of such situations, we introduce the UPF. Here, basically, the picture is that whenever you are designing the RTL, right, it has only the hardware description about all these hardwares. Okay. So now you are asking, okay, we have analog block. Yes, we can have a Verilog AMS or VHDL AMS, that part also. That part only will have the description of the hardware, but not about all of these different power domains and power management block, all this. So to include all the details of these blocks and different power domains, we have to have the UPF. So this is the kind of one shot of the chip today. So in addition, there could be multiple factors like power gating, multi-VDD domain, multi-VT domain, a different threshold voltage domain inside the chip, as well as there could be different cells which are coming with the standard cell package like isolation cell, level shifter, power switches. So these all concepts are interweaved with UPF. Once we talk about UPF, you can think about all the pictures together. Here, whatever I have pasted in this particular slide all comes together when you think of UPF. And these do not come in a particular stage of the design, but throughout the design, all these things will come under UPF. UPF will make space for all of these things inside your SOC design. So we're done with this particular slide. Let's move on. Here, how we can place UPF. Here, first is the entire design. Then, there will be a functional description. As I was saying, that it could be Verilog, it could be VHDL, or it could be something. And another part is the power intent or description that talks about the different power domains, power distribution, etc. Functional description can be written in Verilog, VHDL, Verilog AMS, VHDL AMS. Power intent can be written in UPF and CPF. So in our today's video, now what is a CPF? CPF is from Cadence, and we'll not talk about this in our session. Our focus of this session is UPF. So we'll go throughout our session about the UPF. Now we have the picture where UPF is placed in terms of the description or handwritten code, whatever you're starting with for your design. So let's move on to the next slide. What is UPF? UPF is an abbreviation of Unified Power Format. I already mentioned that, owned by Accelera. any HDL do not have a way to define power distribution or intent of a design, UPF acts like a missing link in the gap, which I already mentioned in the picture which I have shown in the first slide. UPF extends the logic design by adding power-aware functionality. Now, there are two sides. One is power-aware means one is you are designing it as a power-aware, and when you are making the verification, it is also power-aware. So, this makes the sense from designing to the verification, that means from starting to the ending point, you'll see soon. All these things are covered by UPF. So your design is very much power aware. So your design is aware of what power domains are there. So let's move on to the next bullet. It annotates power distribution and power control intent. Annotation means it attaches. As I have shown just slides, in addition to the hardware description language, it is adding power description of the entire chip. It can be defined in abstract level. As I have said, you can start it from the RTL, okay? So it defines no routing or layout information. This is a very, very important part. UPF do not give any routing information at all. UPF specification can be included with the other deliverable as an IP block. So when you are ordering an IP from an IP vendor, it might come with its preloaded UPF inside it, the UPF details. UPF contributes to the power-aware verification. As I have mentioned, not only the design, but also in the verification side, UPF contributes to the power. Once we go through the entire series, right, we will come to this point, how these syntaxes are also there inside the verification part. Now let's move on to the next slide. Types of UPF annotation. First, we start with power supply. When we say that annotation, how many types of UPF annotation we can use in the UPF domain? So first is the power supply. Second is power control. Third is protection. The first power supply is divided into supply net, supply set, and power state. So these three types of UPF annotation can come under power supply. Next, the power control. It could be a power switch. Protection can come from level shifter, isolation. So these are also power intent, but they will be interweaved with the standard cell distribution. They will have their own standard cells for these purposes. So this is the overall picture of the UPF annotation and their types. Benefits of using UPF. To allow interportability across different EDA vendors. Now, UPF is a standard that is given by Accelera and it is not by any particular EDA vendor. So, across multiple EDA vendors and tools, this UPF is standardized. So, when you do a UPF coding, right, and you can port that particular design from one EDA tool to another EDA tool. So, this is the beauty of UPF. UPF supports tickle syntax and semantics. So, it very much tallies with the tickle syntax and semantics. So there could be a lot of tickle commands inside and can use tickle for your wherever. UPF is constantly being evolved. It's not a static language. It is constantly developed by Accelera and versions are coming up and more. So at any synthesis stage, special management cells are inserted in the design as per UPF intent. I see, right, that there are a lot of standard cells which are mapped with the UPF application, right? All those can be inserted at particular stage of the design. At physical design or implementation stage, few cells like clamp cells are added into the design as per the UPF intent. So this is the overall scenario of using UPF. So let's move on. Standard UPF terminologies. Now, we'll talk about some of the terminologies that are widely used in UPF. Before going into the details of the UPF details, okay, you must know about this kind of terminology because these terminologies will come one after another again and again, iteratively throughout the entire series. So better you get accustomed with all of these terminologies. So first is design element. It is an instance of Verilog module, VHDL entity, or a library cells. Design element is an abbreviated to as an element. Okay, so when you say element, it means it's a design element. It could be a module either in Verilog or VHDL, okay, of a cell. Next, design object. A design object is an object that is inside the logic hierarchy. Design objects includes what? Wires, registers, switches, ports, supply, nets, and design elements. Next is the extent, the set of the design elements that comprise a power domain. So this is the extent, the set of design elements that comprise the power domain. So it's related with the power domain. We'll see later when I define different power domains. Okay. Power domain, a collection of design elements that share a primary supply. A power domain may also have additional supplies, including retention and isolation. So this is the definition of a power domain. Pictorially, I have already shown you. Power state table, a table that captures the legal combinations of power states for a set of supply needs. If we have multiple supply needs, there could be a combination and there could be a table, a lookup table that is referred as power state table. So a particular design element in the hierarchy. Regulator, a design element that takes a set of input supply needs and acts as the source for the set of output supply needs. This is a regulator. Next is the current instance, the instance specified by the set scope command. So we are done with this particular slide. Let's move on. So design stages and UPF. So far, we have already discussed about the concept, UPF concept, where it can be used. What are the standard terminologies? Now let's look at, in the SOC design, at what particular stages this UPF is used. First, we are at RTL, yes, and this arrow direction, our flow will go, SOC flow will go forward, move forward, okay? And here, there are two columns. In one column, left column, I'll define the stage, and right hand side, I will show where and details of the UPF. So at RTL stage, we write HDL and we write UPF commands. At synthesis stage, we have get level netlist along with UPF. Next, at PNR stage, we have post layout netlist, okay, that is PG netlist, and we have the UPF along with it. So all these stages, the UPF comes into the picture. So you can see almost throughout the entire design stage, the UPF can come. And now, all these three stages are there. And what we have at the last, we have the VLSI and simulation. At that stage, all these UPF are also checked. So across the entire SOC flow. So this is the entire picture at what stages the UPF is used. So that you get a clear picture. UPF is not something that only at particular stage it is defined. Multiple stages it comes into the picture or it comes into the play. Okay, so all these stages, and at the final stage at the VLSI and simulation, it is also taken care, checked across of the consistency, and a lot of things are there. So let's move on to the next slide. Types of UPF commands. Now, UPF command, there are various UPF command. Now, when I say that UPF tallies with the tickle syntax and semantics, so UPF is basically a set of commands, mostly in the tickle style, or you can say these are tickle commands even, but not the basic or the pure tickle command. These are more advanced tickle commands that is developed for the UPF purpose. Okay, these are not from the very TCLSH commands, but these are tickle commands, and we have 4 types of commands with us in UPF domain. So these are first power intent command. So it defines the power intent of the chip. Next is S.A.I.F. We will discuss about this in the next episode. This is an abbreviation S.A.I.F. Next comes query commands. So these query commands are mostly in the verification stages. It queries different things. So basically this is a kind of object oriented, right? It can query details of our design object. So this query commands goes there. And next comes the test bench commands. So test bench command come when we are into the complete verification stage. So you can see that all these commands will be there when we talk about UPF. Okay. So this slide we are done. Hey guys, welcome to the second episode of Unified Power Format. In this episode, we're going to discuss power domain concept. Next, we'll discuss power domain with a single hierarchical instance. The next we'll discuss is power domain instance with child elements. We'll go down further by creating more hierarchy. Then we will explore UPF power domain creation command. Next, we'll go through a detailed example of the UPF power domain creation command. Finally, we'll discuss about UPF power port, power net creation commands. So, if I sum up, in today's episode, we will be both theoretically as well as with examples, we'll show how you can create a power domain with different hierarchy, how you can connect the power ports and the supply nets for all of these power domains. So without any further delay, let's begin. Power domain concept. Here, this picture I have shown you in last episode, but again I am reinstantiating it because there is a necessity. Let me bring my mouse pointer. So if you remember, this is a power management block which controls the entire power distribution of the chip. And here the different blocks, each with different VDD, and these are termed as different power domains. Now, the matter of fact is that each of these blocks operates its own functionality with the specific VDD they have. So, all internal design elements follow the same VDD as well as the ground each of these blocks. So, let's start the description. Blocks which can be operated with same power supply are identified and tied together. This forms a power domain, as I have shown in the left side picture. A particular power domain can be completely kept on or off, irrespective of the neighboring block. So, the three different blocks in the left hand side, they can operate independently of each other, whether they can stay on or off. A power domain contains a collection of design elements that share a primary power and ground supply net. I already discussed verbally just a few minutes back. The logic hierarchy level where a power domain is created is called scope of the power domain. This scope concept is very much similar to the namespace concept in programming language. So if you are very much familiar with the namespace concept, now you can relate the scope. So here I have not shown any hierarchical design, but in upcoming slides I will show you the hierarchicals. Now there could be different hierarchy levels. The top level, 1 level down, 2 level down, 3 level down. So at which level the power domain is created is called the scope of that particular power domain. Next, any design element that belongs to a power domain are said to be in the extent of that power domain. This extent you can also replace theoretically with the word range. That means anything, any design element that comes under a power domain is said to be in the range of that power domain. So here we use the keyword extent. I used another words for your easy understanding, that is range. So two good things you have to learn. One is a scope, another is the extent. So we are done with these slides. Let's move on. So in these slides, we will discuss power domain with single hierarchical instance. Now you can see there are two texts already present in this slide. First and left hand side, that is power specification, and right side it is logic design. Why I have kept? I am explaining that. So this is a particular block which has a supply port marked in red and through which a pink supply net enters into the block. And it is named as A. The same thing has its logic definition, that is our HDL definition, and also it is for the A. So far, we have discussed that we know about the HDL definition. And in this course, you are learning about the left side, which is a power intent definition, which is UPF. Now, in real world, these two blocks are not separated. These two are the same block. In our mind, there are two blocks. From upcoming slides, I will not create two separate pictures, but I will use one picture as is in the real world. So this is the purpose. I want to merge the concept of UPF and your concept of HDL that is in your mind into one single picture. That's why I have kept separated in the first slide, and from upcoming slides, they will be merged. In this case, the only element of the power block is A, which could be a hard macro or a soft IP. That is an instance of a Verilog module, as I have explained. So the purpose of this slide is done. Let's move on. Instance with child elements. Here, we'll see power domains with child elements. So here, let me show the picture with the mouse pointer. So here, this red is a supply port, and through which the supply net is getting connected, and these are sub blocks, or you can say power domains, and which also have a power port of its in color blue. Okay, both the cases, both are very much look alike with respect to each other. And to put a mirror in between here, you can say this is a mirror image. In terms of topology, I am saying, not in terms of design, in terms of power domain topology. So let me bring on the text now. Here, the scope of the power domain is same as the extent, very much similar, because one is the namespace, that is at which hierarchical level, and another extent or range. So both are same, and both the power domains are neighbors, that is contiguous. Okay. Supply port on A is created using create supply port command. So the red supply port that is at the outer periphery, that is created with the create supply port command. And generally, if it is a top level, right, this will be connected to the ADIO ring in the actual chip. Then supply port is connected to the supply net using the connect supply net command. So this port has to be connected with the supply net. So pink color is the supply net, and that is getting connected with the supply port using the connect supply net command. These are UPF commands. We use create supply net command is applied explicitly for scope A, that is the top level, and implicitly for U1 and U2. So explicit means we are writing it explicitly by words, and implicitly means that we are, by virtue of this command, the U1 and U2 is getting the supply net. So these were explicit and implicit words. Next, supply ports implicitly created on U1 and U2 to connect all the supply nets together. So the blue ports, right, they are implicitly created. I think this picture and the concepts of three different UPF commands, create supply port, create supply net, and connect supply net. These three commands I have discussed here with a pictorial example, and I think it has engraved into your mind. So let's move on to the next slide. Power domain A contains U1/UL. So there is another down level hierarchy, okay, and U2, which do not have another down level hierarchy. So this is the picture. Now you can see here, let me bring on the mouse pointer. So this remains same as the previous picture. Everything here up to here we have seen the change. So there is another hierarchy down there, so which is U1/UA. So these are basically design blocks. And as I have said that these slides, I have merged the concept of the HDL and the power intent, right? So it could be a sub block in the design which requires the power, and this supply net is getting continued through the implicit power ports that is getting created, and it goes up to the U1/UA. Okay. So let's bring up the text now. Here the topology of the logic design is even more complex than the before. Here the power domain consists U1/UA and U2, the two instances in the same power domain which are neither contiguous nor adjacent in the logic design, resulting in a non-contiguous power domain. So this is terminology. This contiguous is a terminology. I have explained what it means, and now this kind of topology in power domain is called non-contiguous power domain. These are new concepts, so you have to learn it, and that's why the picture is there for your clear understanding. In this case, when the create supply net command is executed to create a supply net in the power domain, the supply net is explicitly created in A, that is top level, using the name specified in the create supply net command. Supply ports and supply nets are implicitly created in U1, U1/UA, and U2. So explicitly created for top level, implicitly created for all the hierarchies further down. Okay, and the supply net in U1 connects only to the port on U1 and U1/UL. So this means, let me bring the mouse pointer again. So this supply net is connected here and here. So this is what we are meaning. Although it is clear and evident, but now the picture is with you. But when you are actual design in hand, that time this picture has to exist in your mind and you have to have this text concept along with you to work on. That's why it is explicitly written. Purpose of this slide is over. Let's move on to the next one. Power domain creation command. Now we'll come to the command that we can create a power domain in UPFs. A power domain is created using the command create power domain. The next comes the domain name and next is elements, then list elements means design elements, and the two other are include scope and scope with the instance name. Let's see what are they. The domain name, the new power domain that we are creating. This shall be a very simple name, non-hierarchical. Okay. Elements, use this set of design elements in the power domain. Don't worry, we'll see an example, so you will come to know. Include scope. Include scope, we include the scope of the domain in the extent of the power domain. And final, then scope, then the instance name. Create the power domain within this logic hierarchy scope. So the include means we include the existing scope, and here scope means we create our domain within the hierarchy of the scope. So better you understand this with an example. Let's move on. Here the picture is like that. There is a top. Okay, let me bring my mouse pointer here. Here this is the top block. Here we have E1 and PD1, and inside that level we will create another PD2. That is, this is power domain 1, this is power domain 2. And I also again emphasize that your HDL and your power intent are going hand in hand and in parallel as we have pictorially described. So let's bring the example. Now first, create power domain, space PD1. PD1 is the name of the power domain, then dash elements. Elements is top/E1. Next, we write set scope at this level is /top/E1. So I mentioned that scope means down the hierarchy, at which hierarchy you are defining. You define the scope there, and we are defining with an hierarchical name. Next, we use create power domain PD2. Now as we create the power domain PD2, it automatically comes under the scope that we have set just the line before. So this is how you can create a hierarchical power domain. Okay. That's all for this particular slide. Let's move on to the next slide. Here we'll see another example, and let me bring my mouse pointer again. So this is a top block. This is power domain. This is hierarchical power domain, and this is hierarchical power domain, and we can go on like that, but we will restrict ourselves up to this one. So this way we can go. Let me bring up the example. Set scope X. We are setting the scope X, which is at the top level. Create power domain PDX, and we write include scope. That means when we create power domain X, which is the red box and the left figure, we include the already defined scope that we have just defined in the line before. Next, we write create power domain PDY, and elements is Y. You can see the picture clearly. And next we write create power domain PDZ, then elements Z. So this way we can create a hierarchical power domain. We have gone through two examples to understand how we do that, and this slide is the extended concept of the previous one. So we are done with this slide. Let's move on. Power ports and power net. Now guys, is a very important thing. When you design a chip with the HDL, it will not operate if it do not have the power ports and the power net. So this is the important part of the UPF that we are going to learn. Power comes from the main power sources to IO pad ring, IA power port, and that get distributed inside the full chip or even down to a block. The supply nets are used to connect power port to power pins for each of the cells. Each cell has its power pin, and the power ports and the power pins are connected to the supply net. Create supply port command. This is basically a command, and the following arguments are port name, domain, then domain name, then direction in and out. So a port can carry a power inside or it can come out. So in or out, both the direction can be. The create supply net. We can create the supply net using the net name. Then the next argument is domain, that domain name, reuse and the resolve. I'll discuss detail this resolve one. So first two things, the net name and the domain name is very much clear, easy to understand. And the reuse means that extend the net name as a apply net within the domain name. So why we say this? No new nets are created. Basically, if I exemplify, right, if we have a VDD top, right, and that goes unchanged as a supply net inside sub blocks down the hierarchy, we may not need to change its name if everything will be same as the top level. So that time we can use this reuse. This is done in many of the cases. Next, the resolve one. This resolve is the resolution mechanism which determines the state and the voltage of the supply net from the state and voltage values supplied by each of the individual switches. Default is unresolved. So this resolution means that when a supply need is created, right, how much it is driving. If it is unresolved, that means nothing is properly mentioned. One hot means this supply net is acting like a multiplexer. That means there are multiple outputs. It is supplying one at a time. So it is functioning like a multiplexer. Next is the parallel. Parallel means this supply net is, there are multiple outputs are connected to this supply net and it is supplying all of them together. That is parallel, which is a very in contrast to the one hot. Okay. So this is the meaning of the resolve switch. So here we have discussed about the power port and the supply net, the supply port and the supply net, the similar meaning. So you're done with these slides. Hey guys, welcome to the third episode of Unified Power Format. In this episode, we are going to discuss UPF and corresponding standard cells. UPF versus standard cells mapping. Header and footer switch cells and corresponding UPF command. Isolation cells and corresponding UPF command. Retention cells and corresponding UPF command. Level shifter cells and corresponding UPF command. Power domain and above mentioned standard cell placement. So, if I sum up today's episode, we are going to correlate the 4 special type of UPF command and their corresponding 4 special type of standard cells. We'll go thoroughly in detail and in each of them. So, let's begin. UPF and standard cells. So here, we will talk about 4 type of UPF commands and the standard cell. Majorly these are switch cell, isolation cell, retention cell, and level shifter cell. So in standard cell package, these 4 type of cells are there and these are special type of cells. And in UPF, we have the exact same commands to apply these kind of cells in the actual design. In upcoming slides, we will discuss about all of these cells as well as the corresponding UPF command. So here we have, let me bring my mouse pointer. The UPF command is create power switch. Okay. Corresponding cells are header or footer switch cells. These are picked up from your standard cell library. Now, again, the next command is set isolation. This command picks up isolation cells from your standard cell library. These commands are used in your UPF deck and these are coming into your actual design to implement these commands. So next command is set retention. It calls the retention cells or also known as retention flops from your standard cell distribution. The next command is set level shifter. This calls level shifter cells from the standard cell package. Now, if I sum up, all these 4 commands picks up one particular type of special standard cells from your standard cell design kit. And these are very, very important. So we will explore one by one each of them. And concurrently, we will correlate the command and the switch, the physical standard cell. So let's move on to the next slide. Power switch cell. So here you can see the header switch. Header means it is connected with the VDD. These can cut or join the power to a power gated block. And here VSS is continuous. There is no safe switch in between. The next type of switch could be a footer switch, which we connect in between VSS and the power gated block, whereas the VDD is connected directly. Now, here you can see based on the position of the switch cell, we call it either a header switch or a footer switch. To turn off power supply to a power domain for a particular time of operation, we need power switch to cut the power supply, that is VDD or VSS, to the power domain. So this is the purpose we have our power switch cells. The create power switch command in UPF defines an instance of the power switch in the power domain. The switch is created within the scope of the power domain. The switch is either turned on or turned off as per the requirement. So guys, if I sum up, either it is a header switch or it's a footer switch. In both cases, it can truncate the power to the power gated block. And the corresponding UPF command is create power switch. We are done with these slides. Let's move on to the next slide. Isolation cells. So here, let me bring my mouse pointer. Here we have a power gated block, which we are connected with a always on block. And in between we place the isolation cell and we keep our control in hand whether to isolate or to connect these two blocks. So this cell is called isolation cell. Now let me bring up the text. When power gating method is applied to a design in a particular mode of operation, we might end up with few on domains and a few off domains. If the outputs of the shutdown domain are connected to the active part of the design, then it might lead to invalid signal transmission and crowbar current as a result. This is very evident. If one block is off, another block is on, and one signal is traversing in between, so it will send or receive erroneous signals. This is very, very evident and clear. To avoid this situation, an isolation cell is placed on the output nets of the switched off domains interacting with the active portion of the design. This is what I have just shown in the above picture in this same page. So we are done with the both pictorial and text explanation. Let's move on to the next slide. Here we talk about the isolation UPF command. The set isolation command specifies the design elements in the domain to isolate using the specified strategy. Isolation supply nets can supply a single power net, a single ground net, or both. So, one particular UPF command, it can either specify a power net or a ground net as an isolation net. If only an isolation power net is specified, then automatically the primary ground net serves as the isolation ground net. So one complements the other. If one is specified, other is automatically selected. Next, if only an isolation ground net is specified, then primary power net serves as the isolation power. So in case we specify the ground net as isolation ground net, then the primary power net is automatically treated as the isolation power net. That's the beauty of the UPF command. So at least one of the isolation power net or isolation ground net switch has to be specified unless there is no isolation specified. So when we are writing this command in our UPF text, we have to specify one of these two switches. So this is what we have to keep in mind. Now we're done with this particular slide, so let's move on. retention cells and flops. So here, let me bring my mouse pointer. This is a structure of a retention cell. And here, the most two important signals is save and restore. So this entire setup does what? It stores the last state. If a save signal is sent, it will store the last signal inside it. And before switching off this power block. Once the power comes back to this block, the restore signal is activated. The last save state is retrieved. So this is the purpose of the retention cell. A retention cell is used to retain the data required in shutdown power domain. A retention cell consists of a flip-flop and a save latch and has two control signals, that is save and restore. Save signal indicates when the data should be saved in the latch, which is just before switching off the power. The restore signal tells us when the data stored in the latch should be restored, which is when the domain gets back to the active state. So this is the theoretical explanation behind the retention cell or retention flop, whatever name it is called. So we are done with this slide. Let's move on. The retention UPF commands. The set retention command specifies which registers in the power domain needs to be retention registers. Only the registers implied in the elements list shall be provided retention capabilities. At least one of the retention power net or retention ground net shall be specified. If only retention power net is specified, the primary ground net shall be used as the retention ground supply. And if only retention ground net is specified, the primary power net shall be used as the retention power supply. If both are specified, then these options specify the supply net to use as a retention power and ground nets. So guys, it is very much simple that this particular command has to specify along with any one of the retention power net or retention ground net. Okay, so this will instantiate the retention cells or flops into your design through the UPF tech. We are done with this particular slide. Let's move on. Level shifter cells. So here, let me bring my mouse pointer. Here is the picture. Here is power domain 1, here is power domain 2, here VDD is 0.8 and here is 1. So if a signal travels from this PD to this PD, what happens that here VDD is low and here VDD is high. So the logical 1, 0 will be different. Okay. So we need to normalize these voltage mismatches, and that's why we introduce the level shifter cells. So here we can see if the signal traverses from a low VDD to high VDD, we use LH level shifter, that is low to high level shifter. And if the voltage or the signal traverses from a high VDD to a low VDD one, we use the HL level shifter, that is high to low level shifter. Similar way, there is another PD here, another PD here. Here the left side one is a higher voltage and the right one is at lower voltage. So from this domain to this domain, what happens that we use HL level shifter, high to low. And from here to here we use LH level shifter. So this way we apply our level shifter cells. When two blocks powered with different voltage levels interact with each other, invalid signal transmission and crowbar current generation may take place. So that is what we just discussed. And to avoid this, level shifter cells are placed between the blocks with distinct voltage values. Now this distinct voltage values means it could not be random. For this particular level shifter, the to and fro VDD must be clearly defined. Okay, and that's why we have in the standard cell library we have these specific L2H and H2L level shifter cells specifically designed. Level shifter cell can convert a high voltage level to a low voltage level between the two domains. Level shifters are placed on signals that have sources and sinks operating at different voltages. So here, as we go from PD1 to PD2 or PD3 to PD4 or vice versa, one acts as a source, another acts as a sink. So here we have corresponding level shifters. So we're done with this slide. Let's move on. Level shifter UPF command. The set level shifter command can be used to set a strategy for level shifting during implementation. Level shifter rule can be low to high, high to low, or both. If low to high is specified, signal going from a lower voltage to a higher voltage gets a level shifter when the voltage difference exceeds that specified by the threshold. If a high to low is specified, signals going from a higher voltage to a lower voltage gets a level shifter when the voltage difference exceeds that specified by the threshold. If both are specified, it is equivalent to having specified both rule strategy. In summary, this is the particular UPF command that pulls in the particular types of level shifter from the standard cell library. We're done with these slides. Types of level shifter cells. So here we will discuss different types of level shifter cells. Level shifter position defines whether the level shifter cells are placed in the logic hierarchy. All necessary supplies need to be available in the specified location. Self. The level shifter cell is placed inside the model or cell being shifted. Parent. The level shifter cell is placed on the parent cell or model being shifted. So you can see that this type of level shifting classification is done based on the design topology on which we are placing our level shifter cell. The next topology is sibling. A new sibling is created into which the level shifter cells are placed. So we covered self, parent and sibling. The next one is fan out. A level shifter occurs at all fan out locations, that is sinks, of the port being shifted. Automatic. So for automatic, the implementation tool is free to choose appropriate locations. So guys, we're done with this particular slide. Let's move on. Standard cell placement. Let me bring my mouse pointer. Here you can see this picture I have shown you in last episode. Power domain X, power domain Y, power domain Z, and inside again if we go down we have Y1 and Y2. Here we have Z1 and Z2. So this is PDX, this is PDY and PDZ, and here is our boundary. This is just as our regular UPF structure we get this, and now if I bring on the special cells where they will be placed. So the isolation cell can be placed inside the two interacting power domains, that is here. And the level shifter cell also can be placed here. They can be placed here also if these two are interacting. So based on which domains are interacting, we can place our special cells at these locations. So this is a very simple explanation, and the picture is now clear to you where these cells are placed. With that, we are done with the slide. Hey guys, welcome to the fourth episode of Unified Power Format. And in this episode, we are going to discuss UPF and HDL simulation, UPF function, its category and syntax, UPF supply query functions, supply net and data type in HDL, switching activity interchange format abbreviated as S.A.I.F, System-Verilog Package for UPF, and VHDL package for UPF. So without any further delay, let's begin. UPF and HDL simulation. So in this slide, we will discuss how in a live actual design, any change in the power or ground voltage value automatically taken care by UPF during both design as well as verification stage. So this is our supply port UPF, which has two parts. First, supply state. Second part, voltage value. Now the supply state has off state or on state and full state or partial state. So these are the two states. So any supply port of UPF will consist of all these attributes. The voltage value and full or partial state of a supply net are valid only when its on or off state is asserted. Every time the state or the voltage value of the power or ground nets changes, the power of the corresponding design element is evaluated. Okay, so guys, we are done with this slide. Let's move on. Now let's look at what happens in a design which has two or more power domains which may be turned on sequentially during power up sequence. If both power and ground supply nets are on, the design element instances connected to the given supply pair are turned on. If power or ground supply net is off, the power to the design element instances is turned off. In turned on state, every sequential element and every signal driven from within the power down element is called corrupted because this block is totally off. So any signal going out is unacceptable. Events that were scheduled before the power was turned off and whose target is inside a power down instance shall have no effect. So suppose if there is a block which we have just powered down and some time ago we have started a vector from outside which will operate in time t equal to after the power down sequence, so that will have no effect. So we are done with this slide. Let's move on. In System-Verilog or VHDL, there are three major types of UPF functions which are used to play with any of the power or ground pad or pins of a chip. And here we go. So this is our UPF function. It can be supply on, supply off, or supply partially on. These are the three types. Now, let's go into the detail of each of these functions one by one. First, start with the System-Verilog. A UPF package, supply package, shall provide the following functions. First is a function. Then the supply on, its return type is bit and the arguments are pad name and val, which are string and real as their type. The next is supply off. It has a pad name as the argument, return type is bit, and supply partially on is pad name and value are the two arguments and its return type is bit. Let's look at the VHDL part. A UPF supply package shall provide the following functions. Function, then supply on, then arguments are pad name, then string, then value is real and return type is boolean. Function is supply of pad name, string, then return type is boolean. The next is supply partially on, pad name, then the next argument is real and its return type is boolean. So we have seen all these functions, UPF functions that are very much coherent with the System-Verilog and VHDL functions so that they can operate hand in hand. So that's all for this slide. Let's move on to the next one. Now let us dive into the verification side of the UPF. In this slide, we will see what are the UPF functions that can do a query to a design. So these are the UPF query functions. The first one is get supply value. It will get the supply value as the name suggests. The next one is get supply voltage. As the name suggests, it will get the supply voltage. The next one is get supply on state. It will check the on state. And the final one is get supply state. So it will get the supply state. And these are the UPF query functions which are needed in the verification side. So we are done with this slide. Let's move on to the next one. Supply need data types in HDL. In this slide, we will cover the data structures in both VHDL and System-Verilog that makes room for the UPF supply needs so that the transition from UPF to the Verilog or System-Verilog is a smooth one. So begin with the System-Verilog. Type def, structure, then path. Then we have int voltage and bit state. And then we close it. It has the name supply name type. So it's a data structure that we know where it is well known to us, and the struct keyword is used for defining a structure. So here it is for the System-Verilog. Now let's look into the VHDL. Type supply net type is record, voltage, numeric bit, side, and then we have the bus width, and it gives voltage in microvolt. The next one is state. There is a bit vector and the bus size is there next to it. That is 31 down to 0. And it gives the net state. And we end it with the end record. Then subtype is net state is bit vector 1 down to 0. The defined state bits. These are the supply net data types in HDL. So these are used coherently with the UPF. Okay, so we are done with this particular slide. So let's move on. Supply netting UPF. Let us do a touch base of the UPF supply net command. Here again, which we have talked in episode 2. The create supply net command provides an option that specifies the type of the resolution to be used by the supply net. The following resolution methods shall be provided. As a result, the supply net may be connected to a single output. One hot multiple outputs may be connected to the supply net. At most, one of the outputs may be on at any particular time. So this is acts like a multiplexer. Parallel, multiple outputs may be connected to the supply net. We are done with this slide. Let's move on. Say, power switching vectors are very important in the sense that they define the power up or power down sequence. This switching activity must be coherent between the UPF and the HDL, such as Verilog or VHDL. Hence, the S.A.I.F has come into the picture. Let us understand this in this slide. So let me bring my mouse pointer here. We'll define this thing by text descriptions. But simulator is able to generate the S.A.I.F and we can use to backport that again in power analysis. S.A.I.F stands for Switching Activity Interchange Format. It is designed to assess the extraction and storing of the switching activity information generated by EDA tools. A S.A.I.F file containing switching activity information can be generated using a HDL simulator. This switching activity can be back annotated into the power analysis or optimization tool. So this is the overview of the S.A.I.F. So let's move on to the next slide. System-Verilog Package for UPF. In the upcoming slides, we will take the tour of the UPF packages existing in the VHDL and System-Verilog. In previous slides, we have theoretically covered them, and now we will see them in terms of the actual code. So let's begin our journey. First, we start with the System-Verilog package. Start with the keyword package UPF. Next, we have the type def structure definition, int, and then voltage, and then bit, state. And then we have supply net type. Then we have the type definition of enumerated data type, that is net state is off, on, partial on. This is ASV syntax. And then we have our function supply on, then the pad name and the value as the argument. And the next is the supply off, and the argument is pad name. In both cases, the return type is bit. The next one is supply partial on, pad name, and then value. Supply net type, get supply value, and then name string. So let's move on to the next one. Then we have the real get supply voltage, and we have supply net type argument. Okay. Then the next one is get supply on state. If you remember, we have covered all these things in the previous slides, and now we are seeing them in terms of the code. The next one is the get supply state, then supply net type argument. And here we end the package UPF. So this is the package in System-Verilog that corresponds with the UPF. This must be there, otherwise the two things cannot interact. Two things means the System-Verilog and the UPF. Here we are with the VHDL package for the UPF. UPF supply net. The following type defines the UPF supply net logic type for VHDL. Type, supply net type is record, and then we have voltage IEEE numeric bit signed, then we have the bus size is 31 down to 0. State is again the IEEE numeric bit signed 31 down to 0 is the bus size, and we end record here. So we are done with this one. Let's move on to the next slide. VHDL package. Library IEEE, we all know that is used in VHDL. Use IEEE standard logic 1164.all. Also, this is a very common thing that when we write VHDL code. Use IEEE.numeric_bit.all is the next standard package that we have to use. And then we write the package in UPF is type supply net type is record, and then we write voltage, the numeric bit, and the type is signed, and the bus size is 31 down to 0, and the voltage in microvolt is the unit. So state is again the bit vector, that is 31 down to 0, and type is a net state. And we end here the record. Then subtype net state is off, on, and the partial on. Function supply on. Pad name is string, and their value is real. Return type is boolean. Function supply off. Pad name is string. Return type is boolean. We are done with this slide. So let's move on. Function, then supply partial on. So although it's a new slide, but it's a continuation of the previous thing that we are discussing. Okay. So this is a function supply partial on, pad name is string, value is real, return type is boolean, function get supply value, and then pad name is string, and return is supply net type. Function get supply voltage, value is supply net type, return is real. The next one is function get supply on state. Value supply net type. Return is boolean. Function get supply on state. Value is supply net type. The next we have the return type is bit. Then again we define the next function. Function get supply state. Value is supply net type, and the return is net state. here end package UPF. So the whole package ends here. Okay. So the whole thing is written in multiple blocks and 2 pages, but it is in the single file when you see in actual. We're done in this slide. Let's move on. Hey guys, welcome to the 13th episode of Q&A. We are having a very important topic covered in today's episode from the series of Unified Power Format in VLSI. Viewer Sandeep Vasireddy has asked in the first episode of Unified Power Format, what is the difference between power domains and power modes? So, in today's episode, we will zoom into this particular topic. Stay tuned till the end of this episode to understand the difference. Hey guys, welcome back. We are discussing the viewer's question. Sandeep Vasireddy, who has asked that what is the difference between power domains and power modes. He asked this question in the comment section of Unified Power Format episode 1. So let's start. What is power mode? Power management is a feature that resides in the modern electronic circuits, residing inside the copier's laptop, smartphone, CPU, GPU, monitor, printer that turns off the power partially or as a whole when inactive. This is a very general concept, so that's why I have given all the general examples that you can see around you. Sleep mode is a low power mode for electronic devices. These modes save significantly on electrical consumption compared to leaving a device fully on. So when you are not using a device and the device is on, it consumes the equal amount of power. Instead, if there is a sleep mode, you can put it into the sleep mode and it consumes power. And to be very to the point, the sleep mode is not the turn off or the powered off mode. It is different. Sleep mode is also known by various names, including standby, suspend and suspend to RAM. So these are various nomenclatures, and I have given a lot of examples here like laptop, smartphone, copier, CPU, GPU. So for each of these devices, all these power modes will have different names, even for one particular company versus another particular company. These names will not be the same, although at the bottom they may function the same. So there can be specific names instead of generic names. Thus, you should remember very carefully that whenever you are encountering a mode, this name can be specific to that particular product or that particular company. But however, the same mode of operation you can find in another product which is from another company, and it may still have a different name. Thus, you must remember the things in your mind that the name is not the final one. The mode of operation is the final one. So let's go to the next point. Power mode names may vary from one IC or IP to another IC or IP. Now here when I am speaking about the IC, I mean the already packaged ICs which are selling on the market. And when I am saying about the IP, means when you are working inside the VLSI industry, definitely there will be designs which require IP from a third party IP vendor. So from them, when you buy the IPs and use in your design, the power modes, it can exist there also. Two scenarios you will encounter the power modes. One, in the ICs which are already packaged and selling with DIP or something, all these packaging modes, and they're open market, you can buy them. Or they could be IP when you are designing something inside the VLSI industry as a ASIC design maybe, or maybe analog design, or maybe a mixed signal design, anything. The names may vary. This is the final thing you have to keep in your mind. For any specific IC, please consult the datasheet to understand its power modes and corresponding operation. It's a very straightforward thing when you talk about IC already which is packaged and selling in open market. Definitely, at least for the pin configuration and etc., you have to download its datasheet from their vendor site or maybe from a general site. So this datasheet will contain the details of the power modes of operations. To know the power modes of any IP, you must contact the IP vendor for the respective application note on the available power modes. Here, the factor is different. Here, you are inside the VLSI industry, you are working on maybe on a ASIC project or a mixed signal project or an analog project, and you are buying an IP from a third party vendor. So where you will get all the information about the power modes. You will get all this information by asking the application note on that particular IP from the IP vendor, or in case instead of application note they may have a data sheet of that particular IP, so they can supply that. You can get the power modes detail from there. Sorry folks, because of the text spacing in the bottom. Anyhow, I have narrated it, so I think it's very clear. So let's move on to the next slide. Popular power modes. In this slide I am talking about some popular power modes, putting generic names. So these are not specific, and power modes
for a specific IC or IP, you may find these names to be very specific and they may vary. This is a disclaimer. First, I have to give in this slide. Let me start. Idle mode. What things are stopped? CPU, flash memory, like in a chip, in a ASIC. What is running? There may be a comparator, there may be ADC, and overall there should be a watchdog module, and that should be running. Wake up. When it wakes up and through what? The external, internal interrupt. All these interrupts will wake up the idle mode to an active mode. So these are three category things that you must keep in your mind. What is stopped in that power mode, what is running, and how it wakes up. So this is one general or generic power mode. Let's move on to the next one. Power down mode. Stop all major and minor power blocks. So when we talk about the power down mode, that means that all the major blocks and the minor blocks are powered off. They are turned off. What is running? External interrupt and the watchdog module. There could be some other module based on the design. So I am giving a generic description. So I am keeping the minimalistic things here just for your knowledge purpose. Wake up. To which it will wake up? The watchdog module or the external interrupt. External interrupt, it maybe there is a power switch, you are pushing it and it turning on. Or watchdog, it is signals that can cause the wake up. This is another mode. Let's move on to the next one. Standby mode. What are running? External crystal clock oscillator. If it is a standby, so generally there is a XTEL which works as an oscillator. So that XTEL is running. Wake up. How it wakes up? Through watchdog module, through external interrupt. Uptime is higher than the power down mode. All these things will be there. So standby mode, there is no stop because it is a standby mode. So these are few generic power modes, and if you consult the datasheet, whether it is IC or IP, you will find similar names or maybe the exact names or maybe some variant of them as a power mode. We are done with this particular slide. Let's move on. What is power domain? I have already explained this in the first episode of Unified Power Format. I'll quickly go through this slide. Here, let me bring my mouse. So in today's scenario, this may be a chip. It is a multi-voltage design. So there should be different blocks. So these are power domains. So power domain 1, PD1 operates on VDD1. I am not going to exact specific value, but obviously these and these are not same. So here there is analog block which operates on another VDD, and there is another macro which you bought maybe from the IP vendor. So that IP could run on a third VDD. So I have just given a minimalistic diagram here. There could be many other variations. So I am not going in that direction. It's very simplistic. PD1 operates on VDD1, PD2 operates on VDD2, and PD3 operates on VDD3. And the power management block, this controls the up sequence, that is turn on sequence or the turn off sequence of these blocks, and etc. And this manages the power for all these different blocks. Now, few other things are very important when we talk about the power domain. What are these? Power gating. Obviously, through power gating, all these blocks will get the different supplies. Multi-VDD domain, it is sometimes also termed as multi-VDD domain since we are dealing with the VDD, and you can see the VDD is very much different in the yellow, the green and the maroon block. So it's called a multi-VDD domain. And multi-VT domain. Definitely, when we are working on such power domains, it is certainly logical that we are operating with the VDD, and as per the ITRS technology node, when any particular device, any MOSFET is working on a particular VDD, its threshold is already defined with the ITRS roadmap. You can go to the ITRS website and check these facts by yourself. I'll provide the link in the description. That's why if the VDD is different, it is logical that multiple MOSFETs inside those blocks will have different VT. This is as per the technology roadmap. Now, these things are a few things I have talked about. Some other things which will come at the left side. These cells I'm going to talk about right now. One is already displayed, that is isolation cell. This particular cell isolate, and I have given the detailed description in the UPF series, so I'll not go in detail. But these cells are also needed in today's modern blocks where such multiple VDD blocks are there. Another thing could be level shifter. If you want to exchange signal between two different power domains, say VDD1 to VDD2, that is PD1 to PD2, that means here to here we'll need a level shifter in between, and if a signal exchange is there, we need a level shifter because the basic signal level will be different. Analog and digital, the signal levels are already different because of the fundamental difference. But if it is a digital and it is also digital and the VDD is different, obviously the 0 and 1 levels are different. So level shifter will be needed to compensate this mismatch. Power switches are there. I have also talked about the power switches in the UPF series. So please go ahead and watch those episodes. All are now in the playlist. So you can watch the playlist as in one by one sequence. And I'll not talk any more because I think this is a brief description what the power domains is. You have roughly have a good idea. Let me move on to the next slide. Power up and power down sequence. The power up sequence is the sequence in which the power is turned on for the entire chip. I have shown you already the power management block. This is responsible for this power up sequence, how the power up sequence will work, and let's see more in the bullets. The power down sequence is the sequence in which the power shuts down of the entire chip. So power up and power down is the switch on of the entire chip and switching off of the entire chip. These are two terminologies you are now just familiar with. This includes specification of the time intervals between several steps mentioned sequences. So in the above mentioned sequences, different blocks will be turned on at different time markers. Say PD1 is turned on at t equal to t1, PD2 is turned on at t equal to t2, and this t1 and t2 will be a bit far apart so that one block is fully turned on, the other turns on. So there will be several factors inside the design that they should be powered on, and sometimes dependency of the design should be such that one block should be turned on before the another block because of the functionality. Next point is the power sequence is used when there are semiconductor devices with different power supply voltages, also known as power domains, mixed together in one board or chip. I have already talked about this, comes as a bullet in this discussion page. The time interval specification depending on the device, which can cause problems when applying power to onboard devices with different power supply. So if we do not maintain the proper power on sequence or the power off sequence, it may cause errors or it may cause some data errors. Errors, I mean malfunction of the entire chip, or data which is being stored or data which is being sent, or if it is a in-between router type device, there could be some other thing. So all these scenarios, case specific scenarios, may get affected if the proper power on and power off sequence are not followed. In a general, the power sequence, power to the main block is applied first, followed by the peripheral blocks. So this is, you can understand, the heart of the circuit should be turned on first and then we go towards the periphery. The reverse occurs for power shutdown. Sorry guys for this line. So power on and the power off, the sequence should be exactly opposite. This is general. There could be some difference in some specific cases, but definitely they should be exactly opposite to each other. Let's move on to the next slide. Let us summarize the entire thing, what we have discussed so far. Power mode manages the power supply of various power domains. Second, according to a specific power mode, the power management block distributes power to the various power domains. As per the mode, this power management will control the different power supplies for the various blocks. Power mode is a specification of powering or depowering operation. Understand that switching on or switching off. Power domain is a circuit block with specific power need. Now you can correlate the power mode and the power domain. So power mode is a mode of operation and the power domain which requires that particular mode of operation to be turned on in a correct manner or turned off in a correct manner. I think folks, we are done with these things and let's move on to the next slide.
Hey guys, welcome to the 23rd episode of Q&A. We are having a very important topic covered in today's episode related to the special standard cells described in the series of Unified Power Format in VLSI. Viewer Vandana Sagi has asked in the third episode of Unified Power Format about the fundamental difference between digital buffer and buffer logic level shifter in standard cell. So, today's episode, we are going to zoom into this fundamental difference theoretically along with example. Stay tuned till the end of this episode to understand the difference. Hey guys, welcome back to the computer screen. In today's episode, we are discussing Vandana's question, why level shifter is a buffer? Is there any reason behind being a buffer and not any standard cell? In digital sense, how a buffer allowing high to low or low to high conversion. Now, the last line of this question is the most important part of the question, and here we will focus on today's episode. Vandana has asked this question in the third episode of Unified Power Format. Without any further delay, let's begin. In today's episode, to answer Vandana's questions, we will be covering the below points. What is a digital buffer? Types of digital buffers. What is a level shifter, also known as translator? Types of level shifters. Buffer versus level shifter, a comparison. Buffer versus level shifter, an example. We will then take a small quick look on a available logic level shifter SN74LV1T34. Finally, we will summarize the buffer versus level shifter comparison. This is the menu for today. Without any further delay, let's begin. What is a digital buffer? A digital buffer, also known as voltage buffer, provides either no voltage or output voltage that is same as the input voltage. It draws very little current and will not disturb the original circuitry. To do this, the voltage buffer is constituted with a high input impedance. As a consequence, power source will not be affected. That means whenever we are connecting a buffer to a circuitry from where the current flow or the signal flow is coming inside the buffer is less likely to affect that particular circuit's drivability. It is also called a unity gain buffer because it provides a gain of 1, hence serving no amplification factor. That means the input and the output don't have a amplification relation. A digital buffer is widely used in resistors. So these are very important digital circuits widely used in processors. A typical digital buffer that is used to control multiple data inputs written onto a bus is a tri-state digital buffer, which controls the data flow by tri-state pins. As a student of ECE, you are already aware of what is a tri-state operation in digital. We are done with this particular slide and having a short and sweet snippet of digital buffer. Let's move on to the next slide. Types of digital buffer. Now, the types of digital buffer is very important. This is the slide where you will have the complete idea of buffers so that you can side by side compare it with the level shifters. Because the level shifters also have types. Inverting buffer. So this kind of buffer produces the state opposite to the input. So if the input is high, the output is low and vice versa. Graphically, it is often represented as a triangle with a small circle attaching on the tip. So this is a plain inverter circuit that we use in our digital electronics. Non-inverting buffer. This is a kind of buffer that performs no inversion or decision-making possibilities. A single input digital buffer is different from an inverter. It does not invert or alter its input signal in any way. In other words, the output will be high if only if the input is high. Tri-state digital buffer. The tri-state digital buffer has two inputs, a data input and a control input. A control works like a valve which controls the data flow. When the control input is active, the output value is equal to the input value. Active high tri-state digital buffer. An active high tri-state digital buffer is a buffer with control input high as an active state. Only when the control input is 1, the data transmission occurs. So the active high tri-state digital buffer is a much more specialized tri-state digital buffer. Now you are familiar with the 4 types of the digital buffers, that is inverting, non-inverting, tri-state and active high tri-state. We are done with the classification of digital buffers. Let's move on to the next slide. What is a level shifter, also known as the translator? A level shifter, also known as the voltage level translator or logic level shifter in digital electronics, is a circuit that used to translate signal from one logic level or voltage domain to another. It allows the compatibility between different subchip blocks of ICs with different voltage requirements such as TTL and CMOS. Modern systems use level shifters to bridge domains between processors, logic, sensors, and other circuitry. In VLSI, the most common logic levels are 1.8 volt, 3.3 volt, and 5 volt. However, nowadays the voltage VDD has came down to almost 1 volt or 1.1 volt and even below that in the sub 10 nanometer node. You can follow all these details in the ITRS roadmap. Link will be provided in the description. However, levels above and below these voltages are also used, which I already mentioned. Now, this is a short and sweet description of the level shifter. We are done here. Let's move on to the next slide. Types of level shift. Few slides back, we have seen the types of the digital buffers. Now, let us see what are the types of the level shifters that are available in VLSI design or in the IC market. Unidirectional. All input pins are dedicated to one voltage domain. All output pins are dedicated to other. Bidirectional with dedicated ports. Each voltage domain has both input and output pins, but the data direction of a pin does not change. Each voltage domain has both input and output pins, but the data direction of a pin does not change. Bidirectional with external direction indicator. When an external signal is changed, the input becomes output and vice versa. Bidirectional with auto sensing. A pair of input-output spanning voltage domains can act as either input or output depending on external stimulus without the need of a dedicated direction control pin. The definitions are given to you. The 4 types of level shifters are depicted here. Unidirectional, bidirectional with external direction indicator, and bidirectional with auto sensing. Up to this page, you can already see the classification of buffers and the classification of level shifters are different. Now, let us move on to the next slide. Buffer versus level shifter comparison. Let us draw now a comparison. The job of a buffer is to replicate a digital signal, also increase its drive strength being degraded by other circuitry. So this is the purpose of the buffer. Also, in other words, we can say that this is the function of a digital buffer. As an example, a buffer takes a signal from a microcontroller and reproduce it. Unlike the microcontroller, the buffer has a higher tolerance for being loaded down. At the same time, the buffer will provide more steady output with correct voltage or even with the fastest transition time. So this is one of the use. And the level shifter is similar to a buffer in that it replicates the signal and its drive strength is tolerant to being loaded down. So this is a similarity. This is a very much similarity of the buffering kind of operation between the buffer and the level shift. However, it contains an additional feature which makes it different from the digital buffer is to convert logic levels to the correct voltage value among different voltage domains. So here, actually, the functioning of a level shifter bifurcates from the functioning of a buffer. So we'll take some further details in the upcoming slides. So we are done with this particular slide. So let's move on. Buffer versus level shifter, an example. So here we are taking a case example, not a circuit example, a case example where we will exemplify in detail where the limitation of a buffer and from that limiting point when the level shifter comes into the play. A microcontroller will use 0 volt and 3.3 volt for logic 1 and 0 levels, whereas something you want to connect which will use 0 volt and 5 volt instead. Now, the logic levels of your microprocessor is 0 volt and 3.3 volt and the external circuitry is operating at 0 and 1 at 0 and 5 volt. What happens if you connect the two? The microcontroller will try to communicate with the external circuit. It will send 0 at 0 volt. The external circuit will recognize 0 at logic 0. Everything is fine so far. However, when the microcontroller sends a logic at 1 at 3.3 volt, the external circuit may not recognize the logic 1 since it expects the logic 1 to be 5 volt. A level shifter comes into the picture in this particular situation. Now, we replace the buffer with a level shifter. When the microcontroller outputs goes 0 to 0, the level shifter will output 0. This is same as the buffer. When the microcontroller outputs 1 at 3.3 volt, the level shifter will convert 3.3 volt signal into 5 volt signal. This, the external circuit, sees the 0 volt and the 5 volt and everything works out. So, the limitation of a buffer is well explained here, and from that point of limitation, the functioning of the level shifter to rescue the operation is also demonstrated. This is a fundamental difference. We are done with this particular slide, so let's move on to the next slide. Here, we are just exemplifying a openly available IC. You can also have the datasheet if you look for it, and this is the package chip, so you can sometimes use it in the board level operation also. Without any further talking, let's come to the point. The single supply voltage of this translator are 5 volt, 3.3 volt, 2.5 volt and 1.8 volt VCC. Operating range is from 1.6 volt to 5.5 volt. All these data are picked up from its respective datasheet. If you want, you can Google it and get the datasheet. For up translation, so here comes the level shifting operation. Now 1.2 to 1.8 volt will happen at 1.8 volt. 1.5 volt to 2.5 volt will happen at 2.5 volt. 1.8 to 3.3 will happen at 3.3. 3.3 to 5.0 will happen at 5.0. Now, the down translation will happen like this. 3.3 to 1.8 at 1.8 volt. 3.3 to 2.5 at 2.5 volt. 5 volt to 3.3 volt at 3.3 volt. The output drive of this is 8 milliampere output drive at 5.0 volt. 7 milliampere output drive at 3.3 volt. 3 milliampere output drive at 1.8 volt. Here, looking at the data of this particular logic level shifter, you can easily see that the voltage level translations from up and down to up, and corresponding drive currents are also varying. So here you can practically see the difference of a level shifter from a buffer. So we are done with this particular slide of example. Let's move on to the next slide. Buffer versus level shifter summary. In a nutshell, a buffer tries to recreate the input signal as exactly as possible, whereas a level shifter looks to alter the signal, acting like a language interpreter. A buffer is just an amplifier. It takes a signal, puts a low impedance version of the signal. There may not be an actual voltage amplification. A level shifter will translate between different standards of logic 1 and logic 0 of separate voltage domains. So we are done with the summary, and up to this point, I think you have got the answer of the question what Vandana has asked. We are done with this particular slide, so let's move on. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. If you have some kind of dislikes, put that as in words in the comment section down below, and bye for today.